Let me begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you again, Lord, for these students, for the break we just completed. Pray be with us today. Help us to understand the proofs and statements of Cauchy's Theorem and Cauchy's integral formula. And we pray, Lord, that you be glorified when we do this day, Lord. In your name I pray. Amen. Okay, so let's see here. Well, I'm going to relax here for a second, just read you a quote. What should we make of the integral of phi x dot dx for x equals a plus ib, a plus bi? Obviously, if we're to proceed from clear concepts, we have to assume that x passes via infinitely small increments, each of the form alpha plus I beta, from that value at which the integral is supposed to be 0 to x equals a plus bi, and then that all the phi x dot dx are summed up. In this way, the meaning is made precise, but the progression of x values can take place infinitely many ways. Just as we think of the realm of all real magnitudes as infinite straight lines, so we can envision the realm of all magnitudes, real and imaginary, as an infinite plane, wherein every point is determined by an abscissa A and an ordinate B, represents as well as the magnitude A plus BI. The continuous passage from one value of x to another A plus BI accordingly occurs along a curve, and is consequently possible in infinitely many ways. But I maintain that the integral, computed via two different such passages, always gets the same value, as long as phi x equals to infinity never occurs in the region of the plane enclosed by the curves describing these two passages. This is a very beautiful theorem, whose not so difficult proof I will give when an appropriate occasion comes up. It is closely related to other beautiful truths having to do with developing of functions in series. The passage from one point to a point can always be carried out without touching one where the value of the function is infinity. However, I demand those points to be avoided lest the original basic conception of the integral lose its clarity and lead to contradictions. Moreover, it is also clear how a function generated by an integral could have several values for the same x, depending on whether a point where the value where phi x equal to infinity has gone around not at all, once, or several times. If, for example, we define the log x having gone around x equal to 0 one or more times or not at all, every circuit adds a constant 2 pi I or minus 2 pi I. Thus, the fact that every number has multiple logarithms becomes quite clear. This is from a letter Gauss wrote to Bessel in 1811. And, I mean, this predates the Cauchy publishing these things. But we say it's Cauchy's integral theorem and things, right? Because Cauchy was the first one to really write it down quite explicitly. And many people referred to his work going forward. But I think everybody knows that Gauss pretty much knew these things. And it's fun to study how Gauss behaved. Like, he discovered all these kinds of mathematics, right? And then kind of told us about some of it, and then like later somebody would discover this or that or the other thing, and then Gauss would be like, yeah, I did that 30 years ago, but I didn't bother publishing it. And you can wonder why he was that way, but I don't know. Some of Gauss's statements about teaching would make you never want to teach. He said some very derogatory things about teaching, like he gets nothing from teaching, it's just a waste of time. Students are all dumb. There's some really great quotes by Gauss. I think most people who teach wouldn't really agree with them, but they're fun. But I guess if I was Gauss, everybody else would seem dumb to me too. So, I don't have that problem. Most people seem pretty smart to me. There are exceptions. Right. Oh, I'm sorry, you're not supposed to say that, are you? Every question's a good question. There's no such thing as a stupid question. You teach for a couple years. See if you still believe that. I don't think any honest person can, with a straight face, say there's no such thing as a stupid question. Anyway. Cauchy's theorem. I guess Michael's not coming. I tried to burn a couple minutes for him to push back the useful material, but oh well, we tried. Cauchy's theorem. That seems wrong. Oh yes. Yeah, why? Cauchy's theorem states the following: let D be a bounded domain. What's a domain? Yeah, open connected set, and with piecewise smooth boundary. Partial D. If F is holomorphic if f is holomorphic and continuously differentiable on D, and extends continuously to the boundary of D. In other words, we also have these conditions on the boundary of D, a little bit beyond the boundary of D. Then the integral along the boundary of D of f of z dz is equal to 0. Let me draw a picture just so you don't get the wrong idea about what we're proving. So here's, roughly speaking, a picture of D might be, I don't know, and it could have some holes. Right, so D is this part. So it's bounded, which means I can find a disk of finite radius and fit the whole thing in there, right? I think I've already violated the parameters I set forth for myself. Yep. There. But I guess I probably can safely pan this way. There we go. All right. So there's D. And the boundary of D is the dotted line, right? So that's not actually a subset of D since D is open. And then to say that it extends continuously to the boundary of D, what that means, technically speaking, is you can find a little bit bigger open set, let's say, like this, right? Doesn't have to look exactly like that, but a little bit bigger open set, right, on which those conditions are met, right? So in other words, the boundary of D fits safely inside this green region, all right? That much we're assuming. Okay? So how do you prove this? The proof is basically just by Green's theorem. Let's see here if I can do this. So what's the integral of f of z dz along the boundary? If you write that out in terms of ux and vy and all that, what's this? This is the integral of what? See, we got ux plus I vx times dx plus I dy, right? Which is what? I mean, there's various ways to cast this proof. I'll just work this way. So I got ux dx plus what? Plus here. Oh, what's the right way to do this? Here. Ux dx minus. Oh, I think I'm working too hard here, right? Sorry, guys. I'm working too hard here. Yeah. Let me not be so real in my notation here. Let's say that fine. Ux dx minus what? Minus vx dy plus I times what? Vx dx plus ux dy, right? Now, if I apply, what happens if I apply Green's theorem to this? What do we have? Now, let me remind you what Green's theorem is. We have that the integral of p dx plus q dy is equal to the double integral of qx minus py, right? So I need to do some thinking here about what is the p and what is the q for these different terms, right? So here p is ux, right? So this is q is minus vx, so I got what? I've got minus partial x vx, what? Minus partial y ux dA plus I integral over d of what? Now this time I get partial x of ux minus partial y of vx. Let's see here. Can these terms be simplified? Well, I think so. Let's see here. What's vx equal to? By Cauchy-Riemann equations, right? Which hold inside D, right? So I can apply the Cauchy-Riemann equations, and v sub x is actually equal to negative u sub y, right? So this is partial x, partial y of u minus partial y, partial x of u dA plus I integral d. Let's see here, u partial x, and let's see here, ux is equal to vy, so I'll do partial y of v minus partial y, partial x of v. So I just converted both to u's and both to v's in the second term. And then, since we're assuming that the derivatives, that it's continuously differentiable by, well, anyway, again, by something we haven't proved quite yet, these partials commute. Because, in fact, if it's once continuously differentiable, it has to be twice continuously differentiable. So Clairaut's theorem applies, and you can commute the partial derivatives, and of course these vanish, and you get 0. Sorry, I was a little bit lost at the start of it because it's just not, the theorems we have proved before break about closed forms and harmonic forms and all that stuff, sometimes I haven't internalized some of those things sometimes. So unless I've just presented them, they kind of slip from my mind, which is unfortunate, but on the other hand, Cauchy-Riemann equations are always there. So here's a proof from base principles. I think we should all understand this proof, right? Admittedly, maybe you didn't know that the Green's theorem applies to a theorem with holes, right? Now, Green's theorem, if you have a boundary with holes, then you have to pay attention to the orientation of the boundary, right? So when I say boundary of D here, right, that means I'm talking about the positively oriented boundary, which means the exterior boundary is oriented in the counterclockwise way, right? But the interior boundaries are oppositely oriented. So you have clockwise oriented interior boundaries, and you have counterclockwise oriented exterior boundaries. That's what's needed in order to have the positively oriented boundary. Because again, just a principle thing, if you imagine yourself walking along the boundary, the interior to the thing you're talking about should be on your left. As you can see, if you can imagine yourself, then this is the left, right? On the outside, if you can envision yourself walking on top of the board, right, taking the outside of this way is positively oriented up the upper side of this amoeba-looking thing, then to your left from the counterclockwise oriented. All right, so that's Cauchy's theorem. All right, so and I see what I have done is I've just given you the standalone proof, I think. Well, who cares which one I gave you? Anyway, the notes have more. Okay, so I have an example in the notes here, which I will I think, skip, go on to 4.4. So 4.4 here, we have Cauchy's integral formula, which I will state and then prove. Oops. I thought I threw that out. Come back. I think this is, roughly speaking, the edge of the universe for me at the moment, so I gotta be careful. Is this on screen? Let me check. You'll film on Wednesday? Everyone's afraid to touch the camera right now because it's broken. Oh no, look at that, I've been working off the screen. No! Oh, but not too much off the screen. Let's see, where is that? Oh, I can't even see that green line. There it is. Okay. All right, so Cauchy's integral formula. I mean, this is, you're probably not too shocked to see this theorem, right? I mean, we've kind of had integrals of other things that are going to 0. It's like, yeah, okay, this isn't too terribly surprising, right? It's kind of like integral of an exact form is 0 in a, the appropriate kind of space. But this one here will catch your attention, I think. Theorem 4.41. This is Cauchy's integral formula. Trying to deprive Cauchy of his y today. Cauchy's integral formula. Here it is. And this is the m equals 0 case. We'll talk about m equals to 1, 2, blah, blah, blah as we go on here today. Again, let D be a bounded domain with piecewise smooth boundary. So the same conditions as what? Right, the one we just did, right? And what else are we going to assume? We're going to assume that you have f holomorphic. F holomorphic with continuous derivative in D and near D and a bit beyond the boundary of D. In other words, I'm assuming the same thing I just erased, that this condition is also met a little bit beyond the boundary of D. All right. Then, for each z in D, we have the following. F of z is equal to 1 over 2 pi I, the integral over the boundary of D, f of w over w minus z dw. It's weird. This formula is weird. It says that the value of the function is given by an integral of the function, where you're deliberately dividing by something that is what? I mean, that thing could be 0, right? When z is equal to w. So it's a very strange formula, really. Okay, so here's the deal. We assume the conditions of the theorem, all right? So let's fix a point in D, fix a point z in D, all right? And since D is open, that means Z is an interior point, so we're free to choose some epsilon for which you have a subset, If I have a point, if Z is a point in D, right, then certainly I can pick an epsilon around that, right? An epsilon disk around that, which is what? Inside what set? inside D, right? So D, I don't know, D might have holes, might not have holes, who cares, whatever. There could be some hole in D over here. All right, I don't care. The point is that that disk is inside D, right? And now what can I do? I can define, so I've just picked epsilon greater than 0 such that the disk, modulus of Z minus W less than epsilon, oh, sorry, not Z. Z is a fixed point. I shouldn't use it as a variable, right? So I pick, say W since the modulus of Z minus W is less than epsilon, that's what? That's a subset of D. All right? As I've indicated in the picture. And so we can define D sub epsilon to be what? We can take sort of this, basically delete the epsilon disk about Z from the set D. So I just say D epsilon is equal to the set, the whole domain D with this disk removed. Okay. Is that a domain? Is D sub epsilon a domain? Yes, it is. I removed the whole edge, right? So that makes this, in fact, what I've drawn now, if you take the black dotted, basically this is a hole now in D sub epsilon. So D sub epsilon, if you'll allow me to foolishly shade this as to make my life difficult and everything else I'm going to do with this picture, I'm going to do it. So here's D sub epsilon. It's everything that's in D except what? Except that one epsilon disk around my fixed point Z. You guys with me? All right. So then what? Then we should just smell the roses here a second. What is the boundary of this D sub epsilon set? Because applying the Green's theorem, it's all about the boundary. What's the boundary of D sub epsilon is what? It's the boundary of D, right? Union with what? Let's say the circle of radius epsilon centered at Z, right? In other words, W such that the modulus of W minus Z is equal to epsilon. It's that circle. And to be clear, it should be oriented which way? Oh, wait a minute. Sorry. It's an inside. It's a hole, right? So holes have to be given the clockwise oriented to be part of the positive boundary of D sub epsilon. So this is clockwise oriented. Okay. The sign which that implicitly encodes is important to the theorem. All right, so we let a new function be g of w, and we define g of w to be the quotient of f of w over w minus z. I can do that, right? Notice that that function is holomorphic on D sub epsilon. What point is not in D sub epsilon? W is the variable, right? W equal to Z is not allowed, right? Because that's outside the D sub epsilon set. So if you look at this, you've got f of W, which is holomorphic by assumption on D. The part where it could be bad is deleted, right? So you can argue that this, in fact, is holomorphic on D sub epsilon. And just to be explicit, what's its derivative? Well, g prime of W is equal to, what is it? It's f prime of W over W minus Z, right? Minus f of W over W minus Z quantity squared. What did I do? Differentiating with respect to W, right? Product rule. A little bit of a chain rule there on the second term. right? So we have met the criteria for Cauchy's theorem on this new function g, right? So hence, the integral of g of w dw over the boundary of d epsilon is equal to 0 by Cauchy's theorem. Right? Cauchy's integral theorem, not Cauchy's integral formula, which is what we're currently working on. Students always get these confused. It's important to distinguish these in your mind. Cauchy's integral theorem is a statement about the integral being 0, whereas Cauchy's integral formula is this fantastic result I just wrote here in the m equals 0. Well, it's more than this, but okay. So then what? But that's what? That's the integral over the boundary of d epsilon of f of w over w minus z dw equal to 0, right? Which is what? Which is, so 0 is equal to this, which is also equal to what? This is equal to the integral over the boundary of d of f of w dw over w minus z, right? Then what? Plus the integral around the circle, right? But I'm going to pull a fast one on you here. I'm going to say minus the integral of the circle, w minus z equal to epsilon, counterclockwise oriented. Right, so I put a minus there because I reversed the orientation, right? Yep.
What is the difference from going 0 equals that integral to the next integral? Like I noticed that.
Well, I put the 0 over here for one thing. That's not what you're asking about.
Well, because like you made a whole step of like moving the dw to the numerator and getting rid of the epsilon.
Well, I'm breaking up. That's an integral over the boundary of d epsilon, which has two pieces, right? It's got the boundary of d piece, but it's also got the circle. In the circle, we're actually going to be able to calculate explicitly, as you'll see shortly. This I'm going to leave alone. That's actually what I want a formula for, right? This piece right here is what we're after, right? That's exactly this right here. The other piece is going to work out to 2 pi I times the value of the function at z, as we shall see shortly. So what is this equal to? I mean, actually put it in. What's the, put the value, explicitly here. This is w is equal to z plus epsilon e to the it for t, 0 less than or equal to t less than or equal to 2 pi, right? That's the counterclockwise orientation of a circle of radius epsilon centered at the point z, right? There's the parametric equation for that circle there. So just sidebar here. So let's just calculate. Let's calculate the integral along the counterclockwise integral for a second here. So we have integral of f of w dw over w minus z over the counterclockwise. Again, let's just say minus c epsilon. Good gracious. Minus c epsilon of z, the minus for the counterclockwise. Okay, so that is equal to the integral from 0 to 2 pi of what? F of what? F of z plus epsilon e to the it divided by what? What's w minus z for the parameterization here? It's epsilon e to the it, right? What's dw? It's epsilon I e to the it dt, right? So what do you got? You've got yourself a 2 pi I integral from 0 to 2 pi of f of z plus epsilon e to the it times dt over 2 pi. Sharon's like, why did you do that? What are you doing? Why? What's up with the 2 pi? Why did you divide and multiply by 2 pi? I mean, you can do it, right? 1's 1. But why? What theorem do we know from before the break? I know it seems like infinity time ago, but I don't want to be mean to you to make you remember.
Fundamental.
You're going to make me be mean to you. Fine. The mean value theorem, people, right? The mean value property, remember? This is the average of f around a circle, right? Centered at z. Remember the mean value property for holomorphic functions on a little circle? Radius epsilon. We proved that this is the value of the function at the middle, right? This is f of z. So you get 2 pi I f of z for that. By mean value property for holomorphic functions. So, what we've just shown then is this whole piece right here is equal to 2 pi I f of z, right? So then what? That's it. Because then you can solve, right? You just solve this equation for f of z, and you get this. The proof completed by algebra. Should I write that down? Okay. Well, I run out of space. Fine. So again, we have so today I'm illustrating why I shouldn't do the camera work. Let's see. So what we have is 0 is equal to the integral over the boundary of d of f of w dw over w minus z minus 2 pi I f of z, right? So f of z is equal to 1 over 2 pi I integral over the boundary of d f of w dw over w minus z. And that is Cauchy's integral formula in the 0th case. That's good? Okay. So I hinted that this is just the 0th case of a more general formula. And I will show you the proper proof of this in a second. But if we knew a little bit more analysis, there's a really nice, slick way to derive the further results in terms of what's known as differentiation under the integral sign. So let me show you that. So proceed formally for a second. And what that means is just that I'm omitting a little detail. What I'm showing you is correct, but just an incomplete. And the omission here is one of analysis, right? The fact that, in fact, it does make sense to permute the, well, let me just do it. F prime of z is 1 over 2 pi I partial z of the integral of f of w dw over w minus z. Okay, so the formal thing I was just hinting at was that we can flip the order of these, all right? Of course, this is over the boundary of d. So I have 1 over 2 pi I integral over the boundary of d of partial z of f of w over w minus z dw. what's that derivative? Well, it's not too bad, is it? If you differentiate with respect to z, the w is held fixed, right? So essentially that's just the reciprocal function with some noise, like f of w just pulls out of the derivative, and we get an extra minus from the chain rule. So you would have just minus 1 over the function squared, right? But there's an extra minus that comes from the chain rule, because if I differentiate the denominator, I get a minus 1, right? So that minus and the minus from the reciprocal function derivative cancels to give me a plus, and so what I have is 1 over 2 pi I integral over the boundary of d, f of w over w minus z quantity squared. Right. This, I'll put a box around it here and bring the f prime of z down here. This right here, folks, is the m equals to 1 Cauchy integral formula. Of course, we are not content to differentiate just once. What do you think we can do next? Yeah, if we can do this once, we can do it again. So let's, f prime prime is what? If you don't mind, I'm not going to write out the detail of flipping the integral this time. I'm just going to go do the calculation. What do we get? So this time I get minus 2 from the power, but again, there's a compensating minus sign from the minus z. So I get 2 f of w over w minus z cubed dw. And then how about the third derivative? I get 3 times 2 f of w, w minus z to the 4th dw. Is that enough to see a pattern yet? I mean, we could prove this by induction, but I think maybe you can see that the mth derivative at z should be equal to something divided by 2 pi I integral over the boundary of d f of w dw over w minus z to the what? n plus 1, m plus 1, right? So what goes over here? N. Well, that would make the original be 0, because this is m equals 0, right? So if I need something here. Let me just, so if I put a 0 factorial here, it's cool. Yeah, it's m factorial. You notice that this could be written as 1 factorial. I can erase this 2 and put a 2 factorial, right? This is, I can erase that and put a 3 factorial here. You see? So it's m factorial, yeah. Oh, hey. If somebody asks you why is 0 factorial have to be 1, you can tell them, Cauchy's integral formula. To make it pretty, right?
I get to ask that.
And that way you can, instead of talking about boring things like factorials, you can spend the next half hour wasting their time about complex integration theory. See, it actually has very little, well, I shouldn't say that. Anyway, so there you go. That is Cauchy's integral formula in all of its glory. I mean, can you, I can't impress upon you how weird this formula is, that the mth derivative of the function is related to, you take the function, you divide by the reciprocal, I mean, divide by this particular polynomial, w minus z, integrate over the boundary, and that's the value of the mth derivative at the one point, which is not on the curve, which is inside the curve. That's weird. That is a strange formula. Let me show you how to use it. All right? Now that I'm going to project because I can. Well, I hope I can. We'll find out soon. So guys, once you understand this theorem, part of what it means is some of it's not always the case that we actually need to integrate something from the definition. So the problem of integrating complex functions as we go forward in this course, it's an admixture of the use of theorems and direct computation, and sometimes it's hard to know. I guess from first principles it might be hard to know when you're supposed to do which. When are you supposed to directly calculate from the integral? When are you supposed to apply some theorem to work around the direct computation? And I think the answer to that, generally speaking, is rather complicated, and it's largely, the answer as I know, are largely born from my experience working problems in here, and examples. So the more problems you work, the stronger you are on that issue. But certainly there's lots more. I can't find the stupid notes. Where is it? Come on, where'd you go? What's that? Yeah, I'll do that in a second here. By the way, the example I skipped in section 4.3 is definitely worth looking at. If we have time here, we'll do that. I don't think we have time this semester for me to actually go through these details, but they're important for you to be aware of. The proof I just did for the Cauchy integral formula is general, right? I mean, it's formal, rather. The actual proof is given in the notes here. I actually look at the difference between two functions and explicitly calculate some needed relations between. In short, this is the full proof of Cauchy's generalized integral formula. It's really not much different than what we did for the what we did today. So I don't think it's necessary we go over it. But at the same time, I like what we did today, because that actually, if I tried to derive Cauchy's integral formula from what I have on the board right now, it'd be pretty tough, to get it right. But I think to derive Cauchy's integral formula with, uh-oh, this is going to go badly. We'll see how it goes. Oh, man. I know what, I guess I have to. So begins the story of how I had to buy a new camera. Let's see here. This is not how tripods are supposed to be used. Okay, good. Sorry, I guess for those of you watching online, go look at my notes. Let me make sure you're all here, though. Wait a minute, where's Michael? Michael, go look at my notes. All right, so I'm assuming Michael watches the video later, which is silly. But probably. Let's see. My point, though, was this: we derived the formula pretty easily with just differentiation, right? So I think that'd be tougher to do in the correct formal limiting argument that I have just skipped over here. Okay, so an example. I promise you an example. The integral of sine of 2z over z minus I to the 6th power. All right. Definitely, we don't want to do that directly. I mean, that would be quite awful if you plugged in the parameterization of the z modulus of z equals to 2 circle, right? Circle of radius 2 center to the origin. It's something like an exponential times a sine. It's not actually, okay, fine, it's not actually that bad, but still, this is way easier. So what you got to do is say, okay, well, and what's done, though, you notice I've moved the factorial thing to the other side. So oftentimes when you're actually using the integral theorem, you want to kind of this is often how we use it. It's the integral of f of w dw over w minus z to the mth power is equal to the mth derivative at z, right, divided by m factorial. So put the m factorial on the other side computationally. And of course, the point here is this is something you don't want to integrate, right? I mean, integration's a drag, but differentiation is a walk in the park, right? I mean, so I can trade that integral over the 6th power of z minus I divided into the sign, right, for 2 pi I over 5 times divided by 5 factorial, then the 5th derivative of the sine of 2z function, but at the end of it I got to evaluate at the place where the reciprocal factor is 0, right, which is I. And so you can differentiate sine 5 times. It was what? Sine, cosine, sine, cosine. You pick up 2 minuses, put you back where you started. So I think you end up with 32 cosine of 2z, right? Divided by 5 factorial, which is what, 120? So, I don't know. But then if you're, hey, oh, yeah, there's the 32. But 32 is what? It's, so you can get rid of the 8. I got rid of the 4, didn't I? Why didn't I? 5, 3. Oh, the 2's cancel. The 2 pi I is also there. Oh, I'm sorry. Don't let me get away with that, guys. That 2 pi I is important. We've already seen that in the examples we've done before today, right? That 2 pi I we've seen in our study. The whole day was about 2 pi I, that one day we did, right? And there it is. We did that integral without so much as a u substitution or anything. I mean, there's no integration at all in this calculation, right? That's the power of Cauchy's integral formula. It allows you to integrate without integrating. That's messed up. And there it is. Now this one's a little trickier, but my next example, z to the 4th plus I. And before I even show you the example, I'm just studying what does it look like, all right? So the example I'm going to do is the integral around this blue circle, all right, of a certain function divided by z to the 4th plus I, something like that. And so my point in this setup here is just to show you, okay, so the 4th roots of unity, well, not the 4th roots of unity, but the 4th roots of I are these green dots, and then this red dot. This one red dot is the one that falls inside the blue circle, which is circle of radius 1 centered at 1. Okay, so just keep that in mind as we go to the next page, all right? So if I want to calculate the integral of dz over z to the 4th plus I over that circle, what's my function for Cauchy's integral formula? What's f of z? It's kind of stupid. It's 1. Is 1 holomorphic on that circle and close to it? Yeah, sure. Right? So the question simply becomes that denominator. Is it 0? Right? And then I also have to, well, and I tricked you guys. Is that, is that function, I have to rewrite it as what? I'm supposed to have something like this, right? So you should be thinking of something like f of w over w minus that green root of unity. Which one was it? It was this one, e to the I pi over 8, I think. Is that minus? Yeah, minus I pi over 8. So the f of w actually, it's not 1. I tricked you. Or rather f of z. Oh, and I'm sorry, I've already then the other thing that'll drive you nuts is people also rewrite the theorem like this. This is f of z dz over z minus z naught to the mth power equals to 2 pi I, the mth derivative at z naught over m factorial. Why do we do that? Why rewrite it like that? Why do we bother rewriting it like that? Why would I do that? The reason is simple. It's because I want to be able to integrate integrals in z, not in w. So it's useful to restate the theorem in terms of z, since oftentimes that's how they're given to us, right? And if I have to think through it in w rather than explicitly in z, then it's it's just an invitation for disaster. So you want to, it's helpful to rewrite the theorem. Just like in Calculus 1, sometimes it's helpful to rewrite the basic derivatives in terms of u rather than x for a lot of students. So the f of w here, which is actually f of z, it's the other three factors that aren't 0 inside that circle, right? And since it's just reciprocal, right, there's no differentiation involved. It's just, basically I have, what I'm looking at is, oh man, well, this is annoying. Curses. You see this? This is the term which can be 0, I think. Yeah, when z is equal to e to the minus I pi over 8, that's actually inside the circle. That was the picture on the last page. These are not 0 inside that circle of radius 1 centered at 1. So this is just the thing we actually proved. This is the Cauchy integral formula m equals 0 case, which means I just evaluate the reciprocal of this, at the point which blows up inside that circle, this one. So there's no differentiation needed. This is the m equals 0 case, so you can just evaluate. We can integrate by evaluation. Again, I would like to point out that that is messed up. It's so simple. I mean, I know you might not feel like this is simple, but the devil's mostly in these details up here, right? So the point was this z to the 4th plus I can only be 0 at 4th roots of I, and only that 1/4 root is inside the circle of integration. So these other things don't give you trouble inside the blue circle, and so when I do an integral of a function which divides by factors corresponding to those roots, it's never 0, so the reciprocals, it's fine, it's fine. And then finally, one last little corollary here, and I will shut up. If f of z is holomorphic with continuous derivative f prime of z on the domain D, come on, then f of z is infinitely complex differentiable. If you think about what Cauchy's integral formula tells you, it's connecting the value of the function with the value of the derivative. The value of, right? Look at these formulas. They connect f and the mth derivative. So pretty much what this ends up meaning, if you think through it, is that if you have a once complex differentiable function, you have an infinitely complex differentiable function. There's no twice complex differentiable function, but not thrice complex differentiable function. That's not possible. Again, this is messed up. But anyway, I'll try to talk through that corollary more carefully some other day. I'll let you guys go. I know it's time. So, oh, by the way, your homework's due Friday, because I know you guys are nowhere near done. Why wouldn't there be class on Wednesday next week?
No day.
Yeah. Is there some other test happening that day or something I should know about? Every other teacher has pushed it back? Well, that makes me special. 2 weeks. Really?
Also, I did not count for how long the class was.
Again, I do have your graded. Not terribly carefully graded, by the way. So if you really want to know what was wrong with your regrade, you need to look at the solution. And there's plenty wrong in various folks. Howdy. Not enough.
You actually need to get out of
Good
it.
answer.
Yes. Let's see, I read a book.
Arguably more than I did.
I guess I did. I got done solutions that I should have gotten done before break started. There was that. So those things are necessary. Like, those things had to get done. That's fine. That's true. I don't deny that. But all of the more important things I really wanted to get done didn't really happen.
Chat.
Research, mostly.
Yeah. I remember you talking about that.
How about you? Did you go somewhere for break or something?
Good pouch.
Hmm.
That's in my notebook.
Interesting.
Don't worry, you're pretty little head. Oh man, don't put your fingers in my hair.
Don't put your fingers through my hair.
What?
It's an odd bit of conversation to catch out of context.